All right. Hello, everyone, and welcome to our next JMD-JCISE webinar. So this is another in a long series of really successful, really awesome webinars that the Journal of Mechanical Design has been hosting. And this one is unique in that we are co-hosting it with JCISE as well. So it's lovely to have audience from both journals, JMD and JCISE. Really very appreciative of Leah, who's our special assistant for webinars for the Journal of Mechanical Design. I know she's been instrumental in getting this together, along with our organizers. So let me turn it over to Leah and let her introduce the organizers and get started today.
Yeah, thank you, Caroline. Hey everyone. So my name is Leah. I'm from UT Austin. I'm an assistant professor here in the mechanical engineering department. I'm mainly publishing in the JMD, and I'm part of the IDTC conference and DTM community here. And I've been in charge of organizing JMD webinars along with Carolyn, Emily, and a few others. I'm very happy to introduce that we have organized this JMD-JCISE joint webinar. This was an initial idea that was brought to me by our associate editors, Jenghui Shah and Babak Haidari. They are going to be the ones who will be introducing the topic briefly before we get started. But they were very excited about this idea, and we're happy that we're able to bring together both communities and introduce some of the cool works that's been going on within this community. So I'll hand it over to Jenghuit for more introductions about the topic.
Thank you very much, Leah. So I'm going to share my screen. Can everybody see my screen?
Yes.
Yes.
Okay, great. Yeah, good morning, everyone, and good afternoon from everywhere around the world. And this is going to be probably the first webinar that Leah is helping organizing. Hopefully, we didn't give you a hard time, Leah, organizing this webinar. So first of all, I would like to first thank the strong support from our GMD editor office, especially Dr. Sibersat, and also Dr. Yan Wang from JSISE in supporting this idea of running a particular session on network science and graph theories in the design community. And also thank for my colleagues, Dr. Babak Haidari from Northeastern Universities, working with me and Leah on making this happen. Thank you all for your support. So before we go into the details of the presentation, I want to quickly introduce our thoughts behind the scene and why we want to run this webinar, and a little history of the research in both JSISE and the JMD community. So basically, we found that there has been a long history and a strong interest in answering research questions in systems, especially system design, system engineering in the design community. And back in 2011, we had this special issue organized by Dr. Panos Babalamros and on design of complex engineering systems. And later on in 2020, and we had another special issue on the topic of design of social technical systems. And two special issues were both on GMD. And also later in the design science, we also had a thematic collection, which is similar to a special issue on the topic of networks. So it's a particular focus on network-based modeling and analysis in design. And through the years, we observed that network have become a foundation and a universal language and a representation for us to understand complex relations that span engineering domains. And we found this quite useful for solving many fundamental problems. This is one of our motivation to really think about, okay, now probably it's time for us to rethink the role of network science, graph theory, and their integration with AI, and driving us to organize a special issue in JSISE, and then later on the webinar through the GMD webinar series. And also, we found that there is a convergence we saw in the literature of network science and multi-agent system and dynamic game theories, and it's transforming how we present, design, model, and optimize complex systems. It's quite powerful. And especially recent advances, we notice that there has a very synergistic integration between network science, graph theory, and AI. So there has been emerging technologies such as graph neural networks, graph reinforced learning, and the integration into generative AI. And we have seen models called Graph GPT, for example, and multidimensional network theories. So are rapidly expanding the toolkits we have, and also shaping how we are going to model the system, and is really pushing forward the methodological frontier. And the last point, we also notice that as AI agents becomes integrated into teams and organizations, and adaptive network methods grow increasingly and essential for studying dynamic and highly heterogeneous social technical systems. And I know Dr. Babak Hidari has recently also had some work on this, and we're really excited to see some of the colleagues working in the same front line on these topics, and we are happy to talk offline. And with this, I would like to introduce this special issue, and because all these motivations, and we started this special issue through JCISE, and we discussed with Dr. Yan Wang from JCISE of these ideas about 2 years ago, and through the organization and the collection of the papers, we received about like 15 papers, but because of the publication schedules and the review cycles, we were able to finally include the net papers in this special issue. So this special issue is one of the pool we considered of inviting the papers for presentation for today. So it's been a hard decision. So I just want to briefly mention that there has been so many good papers, and we found that many topics we found on JMD and JCISE in the past 2 years. That's one of our criteria. We select papers. We want to invite the authors to present one of the most exciting and state-of-the-art work in their recent studies. So we picked 5 papers from JMD, we picked 5 papers from JSIS from the special issue, and we finally decided and selected 5 papers considering the diversity of the topics, for example, and different techniques, just like I just mentioned. And then this year is our main content and invited speakers for this JMD-JCISE joint webinar. And we're very fortunate and very happy to have all the authors here presenting their work. So with this, I would like to conclude my presentation and hand over this to Leah.
All right, thanks, Jinghui. All right, so I'm gonna start introducing the topic or different papers that's been selected, which the authors are shown here, our speakers are here. So I would like to introduce the first paper, which is by Dr. Syed Bayat. This is a paper called Can Graph Neural Networks Help Identify Promising Thermal Management System Architectures Among Vast Numbers of Possibilities? He is from University of Michigan, and let's welcome him for the first talk.
Thank you. Let me share my screen. Can you see my screen?
Yes.
Okay, great. Yeah, hello everyone. My name is Saeed. I'm currently a postdoc at the University of Michigan, but this work is from my PhD at the University of Illinois. So first, I will go through the problem definition, and after that, I will explain how I use graph neural network to address some of the issues that I will mention here. So here on the right, you can see the system. Here we have several heat generating devices that are mounted on these cold plate heat exchangers. These devices generate heat, and thermal management system regulates and dissipates that heat. In this system, the coolant is stored in a tank and is pumped through a network of branches. As you see here, these branches have valves and can also subdivide it into sub-branches, as you see here. And in this system, as the coolant flows, it absorbs the heat and it transfers it to the thermal sink via a liquid-to-liquid heat exchanger. So here the aim is to find the optimal talent management system such that the performance is maximized while all constraints are satisfied. An objective here is we call thermal endurance. It means keeping the system operating as long as possible while satisfying temperature limits of the heat generating devices. And we have two design variables. One of them is the flow rate of this coolant. So we assume that we can actively control these valves such that we can control the flow rate as a function of time. And the other one is a topology or configurations. For example, here, as you see, these heat exchangers can have various configurations. They can be in series, in parallel, or hybrid. So we have these two design variables to maximize the thermal endurance. And because this is an optimization problem, we need to also have the dynamic of the system. So we develop a Python code that, given a graph, it can give us back the dynamic graph. For example, here, for just a really simple case that we have just one CPHX node, as you see here, you can see different dynamics. For example, we have convection, advection, and bidirectional convection there. But the code that we develop is kind of work for much really big graph. So given a graph, the code gives us back the system dynamics. And that's based on that, actually, we run the optimization problem. So the thing is, in this slide, I will go through the motivation. As I mentioned, we want to find the optimal configuration and optimal flow rate such that we can maximize the thermal endurance. And one approach to find the optimal configuration is to enumerate all possible architectures. For example, on the right, I'm showing a system with just 3 CPHX nodes. In this system, we only have three heat exchangers. As you see here, number 1, 2, 3 are actually our heat exchangers. As you see here, if we have only 3 devices, we have 13 different configurations. For example, in the first one, all of them are in parallel, or we have in series, or like these shapes. So if we want to do enumeration, it means that for each of these, given a heat load, so here D1, D2, and D3 are the heat load of these nodes. So if the heat loads are determined, then for us to find the optimal configuration, it means that for each of these 13 different configurations, we need to run the optimization problem, find the optimal flow rate, compute the objective, and then rank them based on the objective, and choose the first one as the optimal solution. However, as the number of component increases, for example, here we have 3, but as the number increases, the number of possible configuration grows exponentially. So that's why we cannot use the exhaustive search to find the optimal configuration. And because of this, we try to use graph neural network. But before that, I want to mention what we have found through some initial studies. So we found that we saw a strong link between topology and the performance. For example, as you see here, as I mentioned, D1, D2, and D3 are heat loads of these nodes 1, 2, and 3. And through some initial studies in this paper that I mentioned here, we realized that there is some connection between the heat loads and the optimal graph. For example, when the heat loads are close to each other or almost the same, we realize that among these 13 different devices, 13 different configurations, the first one was the optimal solution. Or for example, when heat load of node 1 was much higher than node 2 and node 3, we realized that this was the optimal configuration. It also makes sense. For example, here, if the heat load of node 1 is much higher than node 2 and 3, as you see here in this configuration, heat load of the node 1 is really close to the tank. So it gets the maximum or cool flow rate of the tank. That also makes sense if you think this way. So because we understood this relationship between the heat loads and also the optimal configuration, so we said that, okay, now instead of doing exhaustive search, let's use a graph neural network to predict the optimal configuration. So in this way, we can reduce the computation time a lot. So that's why we use graph neural network for this problem. So as I mentioned, we have a graph. We have a system, we model it as a graph. We represent each graph as a thermal management system, and we use graph neural network here. We define the features for the different nodes. We have junction node, we have CPHX node. To define different features, and we use GNN to predict the system level performance that actually determine endurance or objective. So the goal again here is to, given heat loads, it can predict the objective for us. And in this way, it enables fast screening across vast design space. And here I'm showing the internal structure of the GNN. So we have features, we have 3 layers, each layer 16 neurons. We have 10H activation function. Then we have global layer, and in the end, we have a linear layer without activation function. And again, the end result is T-end or objective. And in this paper, we tested different GNN models like graph attention network, graph convolution network, or MLP. As we see here, for both training data and test data, the graph attention network works better. That's why in the results section I will present next, I use graph attention network. So here I go through the result. Again, in the paper, you can see much more result, but because of the time, here I'm only showing one of the results. So here we are investigating GNN performance of graphs consisting of 6 nodes. It means that we have 6 CPHX nodes. And if we enumerate these 6 nodes, we need to actually, if we do an exhaustive search, we need to run and optimize about 4,000 different graphs. Actually, I did that to compare it with graph neural network. But if we want to do exhaustive search, we need to run this number of optimizations. So in this plot, the horizontal axis represents these indices of 4,000 different configurations, and the y-axis shows the objective values. So the higher means the better. And here, the green square shows the predicted best solution from the graph attention network. And the green diamond shows the true best solution based on the exhaustive search. So as we see here, the green and the red one are pretty close to each other. And we define a metric, we call it JSUB. JSUB shows the relative objective value of predicted optimal graph, the red one, to the true optimal graph, the green one. As we see here, JSUB is about 0.98. It is pretty close to 1, which means that our GNN had a good performance to find the optimal objective value. Also, if we count the number of the small nodes, the small dots between the red and the green one, the number is 33. It means that the predicted best graph is ranked 33 out of these 4,051 graphs. So it means that if we want to find the true optimal configuration, then instead of optimizing or running 4,051 cases, we just need to consider 33 different cases. So in this way, we could decrease the number of enumeration, number of exhaustive search by more than 99%. That's again the true value of the GNN here. In the end, I will go through the conclusion. So as I mentioned, as the number of configuration grows exponentially, full enumeration becomes infeasible. Although I didn't go into detail, but we trained the GNN based on only 30% of the data, and we predicted the performance on the remaining 70%. In the paper, it was shown that we can achieve about 92% reduction in computation cost. We could identify near optimal designs with high accuracy, and this approach enables efficient identification of high-performing configuration without exhaustive search. That's all. Thank you.
All right, thank you. All right, so before we begin, I realized that I didn't give you guys a quick introduction. So the first 3 papers that will be presented will be JMD papers, and then the next 2 will be from JCISE. And each speaker will have about 10 minutes to present, and then we will hold the Q&A session until the end, but feel free to use the chat to post questions for the speakers. Okay, all right, thank you, Syed. So the next talk is by Giota Paparistodimou from Base Systems. I'm sorry if I butchered your last name, but she will be speaking on the paper called Dynamic Dual Layer Network Resilience Assessment as a System Architecting Tool. So let's welcome Giota.
Yeah, sorry, I thought it's 20 minutes, so I prepare a bit more, so I will try to go a bit faster. So I am Yoda Babaristan-Dimo, I work in BA system, and I will try to present you the methodology we created that we are using as a system architecting tool to assess resilience at the early stages of design. So this is the overview of the presentation. I think we all know why resilience is important. We have big, complex, and some case unpredictable disruptions in the systems, the modern systems we are seeing today. We have a rise in automation. We have unpredictable also evolution of the technologies of the systems. And there is a clear need that we need tools in the engineering design to push the analytical and objective assessment and quantification of systems at the earlier stage. So we want a high level representation and analysis of the system at early stages. So here comes the network science that offers us this high level of representation. So the tool that we have created and was presented in the system takes a given system architecture option, the one that the designers and the engineers have already formulated and considered at early stages and is under consideration. And the tool essentially performs the analysis of that and generates a resilience score and identifies specific disruption instances that will lead to vulnerabilities. So this method, we have computationally implemented it in MATLAB. And given that our method doesn't have an automated generation stage, we need a number of inputs from the user in order to translate their system architecture option. So in the start, we need to define what is the functional logical architecture of this system, how this is reflected in the spatial dimension. We take the physical spatial dimension into consideration. We also define what is the level of redundancy in this system architecture, and we want to know what is the normal operational system architecture topology. And we also use the concept of source and demand nodes, and we want to understand what is the demand nodes that they need to be live and operational. And also we also are able to define the scale of disruption, the strength of the disruption that such a system architecture is able to withstand. And also regarding the redundancy design and the recovery, we want to understand how these redundant standby components will become available. So we have a startup time for these components. And in order to assess resilience, we want to understand what is a minimum acceptable performance for this system and what is a satisfactory performance. And we also want to understand within how much time post-disruption that system should be back and running. So I gave you an overview of this. I will discuss them to the next page. So here I started discussing about the network modeling we are performing. So we can see the functional network, that is the logical network. And we define in green is the operational nodes that we are expecting that they are live and operational in normal situation. And in yellow is the redundant. So it's the redundancy we have designed in the system to be able to recover through disruption. The functional network is the components, and we can see the physical network is essentially a two-dimensional grid. I will discuss also in the case study. So we can imagine is X and Y is where the components are located in a physical spatial space. So here we are simulating a disruption. The way we simulate disruption are in the physical grid. So it's in the physical network. So one physical disruption is happening, and we reflect this up to the functional network. So the purple shows what is disrupted, and we see in the functional network what is incapacitated, is not live anymore. And we can see the green and the yellow. The green is live and the yellow is standby. And then we move to the recovery. So as I said, we have the redundant components that have been designed, and however, we have the startup time. So if a redundant component, we expect that in 0 minutes it will become alive, then becomes yellow and green immediately post disruption. But other components, they need some time to start up. They will not be immediately available. So they will become available in time steps post the disruption. So this is the overview of the methodology. The dynamic aspect of the methodology is essentially in network science is the time-varying network modeling. We do a series of various static network states analysis, and in discrete points of time, or in other words, in network science, we found the term temporal network, and we simulate, we do a simulation using this series of static network snapshots. And for each of these snapshots, we calculate a performance metric for each of the snapshots based on the definition of source and demand. So the metric is directional, so there is a specific directionality, and we calculate the ratio of level of direct connectivity between the source and demand, and we relate this to the required performance. And after a disruption, due to the redundant components, that they become alive, the network is reconfigured, and for each of these snapshots, we calculate the performance metric. So the disruption strategy, as I discussed, happens in the physical network and is reflected in the functional. We do a combinator in disruption. So for one component, we will do all the components, but for two components, we will only do physically adjacent components that are possible to be adjacent. So in that way, also our computational effort is manageable for the method. So the recovery strategy relates with the standby redundancy and the time that this standby redundancy comes up. And we wanted specifically to create this recovery strategy as a parameter of the design, and for the users and the designers to be able to alert it, because we wanted to analyze and investigate how the redundancy we are designing improves or affects, has a direct effect on resilience. So we wanted to study this interplay and how, if we design our recovery strategy in a different way, how this will affect resilience. And we created this resilient metric that relates to two principles. We have a principle that the performance must remain above a minimum value immediately post disruption, and the performance requires to recover into satisfactory level within an acceptable time. And the reason we created this resilient metric is grounded back to the graceful degradation concept of resilience. So immediately post disruption, a resilient system should be able to manage a performance. So for example, in ships, that the case study relates, in immediately post-disruption, commercial ships are regulated to have available emergency lighting, to have communication, to have emergency pump. Same naval ships under immediately post-disruption are required to have specific capabilities related with survivability. So here I will give you a quick overview of the case study we have created that relates with a power and propulsion system of a naval ship. So this is 3 design variables that we decided. Essentially, these are system engineering questions that designers may debate at the early stages of deciding the system. Like, for example, here is, should we put batteries? What is the style of redundancy? How many main sources we should have? So, for example, here we can see this is the style of connectivity here and here. I will show you more options after. This is, should we have additional batteries and how they will support. And these are the main sources, power of generation. This is a systematic way that we have created for the case study, and in order to be able to systematically analyze the options. This is the definition of the performance criteria. Essentially, we are saying here we want these consumers, and these are the demand components, and immediately post disruption, we want them still to be receiving electric power from the sources. And this is within an objective time. Post disruption, we want these consumers and these demand components to have connectivity with the sources. This is essentially the physical grid. So the zone and the deck creates the physical network grid, and this is where the components are located. So here I want to show that obviously we use to collect our results and to define the system architecture option under consideration. We use a very popular engineering design methodologies method and design structure matrix essentially. And here this represents this schematic here. Essentially, diesel generator 1 is connected with a switchboard 1. We can see here in mathematical terms, in network science, this design matrix is the adjacency matrix, and then we translate it into network. So the columns that are here is how we collect our input. We annotate this is a source, this is a demand component, and here we say this is operational, this is standby, this is what is the time to start up if it's on standby mode. This is how we define this component is located in this zone and in this deck. And for example, the variable we're debating here is this connectivity. What is the best? I will show you. So there is these options. We can have connectivity and additional redundancy in connections in the NDC levels, or we can have them in the consumer levels. These are design questions that we engineers debate in the start, how many main sources we can have, or if we will have in our design additional batteries, for example. So we have generated these alternative options. We used our tool, and the tool has generated for us the results. So the tool has generated for us the results and is saying to us that the option 5 is the highest resilience. This is an expected result that also subject matter experts could expect. The interesting results is the option 1, that is the second best result, that actually is the resilience a bit less, but there is more components to the design. So obviously additional components, they have other implications. There is cost, complexity in the ship case, in the ship design case, there is weight and stability considerations. So we can see there is, the return or resilience needs to be considered if it's worthy these additional components and complexity for the amount of resilience that we are gaining. Also, we can see here that the strength of the disruption has more obvious results in resilience, where if we are just removing one component, the behavior on resilience is similar. We also see here an interesting result is that the redundancy we put in the consumer level, it goes more beneficial than the redundancy we put on the NDC level. And we can see also another result that an option with batteries and redundancy at the consumer level had the same, at the NDC level had the same resilience and as an option without batteries and redundancy at the consumer level. Obviously, such findings have caused development and other implications that are important for designers at early stages. So we developed this tool to support analysis of resilience at early stages, to support design questions related to redundancy and architectural patterns. and to be able to early identify vulnerabilities. Our future work will focus also more on the generation stage and to expand to optimization, and perhaps we can combine reliability considerations also in our disruption. So thank you. And
Yeah, thank you, Joda. All right. So this is the last JMD paper. This is by Yuliang Li from Donghua University. The paper will be called An Integrated Task Parameter Network Framework with Sensitivity Mapping and Path Enumeration for Objective Dependency Analysis in Complex Design Processes. So Yuliang, you can take over.
Okay. 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 Hello, everyone. I would like to thank the SMG, JMD, and JCISE editorial board for the invitation. I'm Yuliang Li from Donghua University in Shanghai. Today, I will be presenting our recent work on complex product design. Consider modern engineered systems like electric vehicles. The design tasks are tightly coupled. A small change in a single parameter can trigger a massive chain reaction. So how do we currently measure these connections? Often we rely on expert intuition, but let's be honest, that can be quite subjective. Our research offers a new approach. We developed a data-driven framework. We did dive into this. This is the content for this talk. It includes 7 parts. First, let's look at the research background. For years, the design structure metrics, like this classic figure on the left, has been the standard tool. It helps visualize how tasks are connected. However, for today's complex systems, traditional DSM methods face 3 major limitations. First, subjectivity. It relies on expert scoring. Different engineers often give different scores for the same link, leading to inconsistency. Second, constant granularity. A hybrid granularity of DSM is often needed for management of design process and solving of design problems. Third, lack of nonlinearity. It simply models dependencies between tasks or entities linearly. So the key challenge is how do we move from subjective task-level guesses to an objective data-driven task parameter framework. Let's see how current research attempts to answer this. Following that challenge, let's look at the current literature on parameter level evaluation. The first approach relies on analytical equation models. While they use exact formulas, they are often unrealistic for modern complex systems. In reality, we usually face black box models where explicit equations simply don't exist. The second approach is local sensitivity analysis, or LSA. It uses data to measure local gradients, but here is the catch. LSA only captures local perturbations. It completely fails to track global cascading effects. So the research gap is clear. Existing methods are either mathematically restricted or locally confined. There is a missing need for a global data-driven metric. This leads us to our proposed method. To solve these challenges, we propose a four-stage framework as illustrated here. Stage 1 is about opening the black box. We decompose high-level tasks into specific parameters, decision parameters, intermediate parameters, and target parameters, building a detailed task parameter network model. Stage 2 focuses on quantification. We apply super sensitivity analysis to measure dependency strings. To handle complex black box systems, we integrate Kringen surrogate models for accurate fitting. Stage 3 addresses propagation. We use depth-first search to trace our influence paths, calculating both direct and aggregated impact strengths. Stage 4 is the optimization. We leverage these metrics to adjust task partitioning, maximizing internal cohesion and minimizing cross-task coupling. Now, let's walk through each stage in detail. Let's dive into stage 1, opening the black box. As you can see in figure 3, we move beyond the traditional black box view. Instead of treating a task as a single dot, we decompose it into each core component, decision, intermediate, and target parameters. The key innovation is in figure 4. We model tasks not as isolated nodes, but as communities of parameter nodes. Notice the edges, they represent direct information flows. Critically, we transform static constraints into dynamic directed flows. This allows our computational model to track exactly how a change in one parameter triggers a change downstream. So in essence, a task is now a community of parameters. But how does this work in a real engineering project? Let's look at our case study. To demonstrate this, we applied our method to a permanent magnet synchronous motor design. On the left, we took the 7 core design tasks and decomposed them using actual physical equations. This process captures every functional relationships, turning high-level engineering logic into a data structure. This is resulted in the network you see on the right. Look at the complexity. This is the real parameter relationship network of the motor. The nodes represent parameters color-coded by their original tasks, and the arrows show the direct flow of information. We've successfully mapped the topology, but topology alone isn't enough. The next question is how strong are these connections? How do we quantify the weight of these edges? To answer that, we move to our sensitivity analysis. Now, let's move to stage 2, quantifying the weight. On the left, we use super global sensitivity analysis to capture nonlinearities. We don't guess the importance. We calculate the various contribution of each parameter. The super index directly tells us how much a specific parameter, like motor power or gear ratio, drives the output variance. This gives us an objective mathematical weight for the dependency edge. But what if we don't have a neat equation? That's why the right side comes in. We handle empirical data using Kringen surrogate models, as shown here. We take discrete samples like this, 110 LH points, and train a continuous model. The result is highly accurate with an R-squared value over 0.9999. Once we have this continuous function, we feed it back into the super analysis. In short, whether we have equations or just data, we can compute the precise bidirectional weight for our network. With the network weighted, stage 3 calculates the macro-level dependence between tasks. In complex systems, indirect paths are just as important as direct ones. To capture this, we use depth-first search to enumerate every possible directed path. Let's look at our PMSM case on the right. Calculating the impact of the length to diameter ratio on the target parameter F15. Our DFFS found 9 distinct paths. The math is straightforward. The strength of a single path is the product of each edge. sensitivities, and the total impact is the sum of all paths. Finally, we are aggregate all parameter pairs to get the final task dependency. Here, task 1A to 1B is 0.94. This ensures we capture the full picture, including indirect influence, which traditional shortest path algorithms would completely miss. Applying this logic across the entire system, we generate these purely data-driven forward and backward dependency matrices. Look at the table on the right. Unlike traditional binary DSMs that only shows ones and zeros, our matrices offer high-resolution quantitative precision. The forward matrix guides execution sequencing, while the backward matrix reveals potential iteration risks. To validate this, we compared our results with assessment from 7 senior motor design engineers. The alignment is striking. Our data-driven matrices achieved nearly 90% agreement with their expert judgment. This proves the method is not just theoretically sound, but practically reliable. With this robust foundation, we are now ready to optimize the task structure. Let's move to the stage 4, task clustering. Moving to stage 4, we refine our task division. As you can see in the diagrams on the left, our concept goal is simple. We want high cohesion, meaning parameters inside a task are tightly connected, and low coupling, meaning tasks are as independent as possible. But how do we objectively identify which tasks are purely structured? We use a three-step mathematical evaluation shown on the right. First, we calculate the absolute cohesion of a single task. Second, we establish a global baseline by calculating the weighted average cohesion across the entire project. Finally, we divided the single task cohesion by the global average to get the task cohesion coefficient, or TRC. This TRC is our data-driven trigger. If a task has a significant low TRC, it means its internal parameters are weakly connected compared to the rest of the project. Once identified, we use three strategies. That is task merging, task splitting, or parameter reassignment. This systematic approach ensures that our task partitioning is not based on intuition, but on objective quantifiable metrics. Now let's look at the actual optimization result for case 1. The model design using the parameter reassignment strategy. Please direct your attention to the before and after tables on the slide. First, look at the dependency strings matrix at the top. If you follow the red arrows and boxes, you will see a dramatic reduction of diagonal values. For example, the dependency between task T1C and T1B drops to exactly 0, meaning they are completely decoupled. Additionally, T1F's reliance on T1B drops sharply from 0.66 down to just 0.02. In practical terms, this eliminates sequence bottlenecks, allowing these tasks to be developed in parallel. Second, look at the task cohesion tables at the bottom. This measures how well integrated the parameters are within a single task. Again, looking at the red box, the cohesion coefficient for task T1A surges from 0.7 to 0.93, and the task T1G jumped from 0.36 to 0.78. In conclusion, these numbers clearly prove that methodology successfully achieved the core goal of module design, minimizing external while maximizing internal cohesion. To summarize, our research delivers three core contributions. First, objectivity. We replace subjective approach scoring with rigorous data-driven sensitivity analysis. Second, granularity. We moved from treating tests as black box to mapping transparent parameter level networks. Third, Axin method has real engineering. It significantly increases the modularity, and our future will focus on evolving this model to support dynamic real-time update during the ongoing design process. And this concludes my presentation. Thank you.
All right, thank you. Okay, so let's move on in the interest of time to our JCISE paper presentations. The first talk is on toward early design modeling and simulation of distributed situation awareness by Daniel Hurst from NASA Ames Research Center. We're very happy that we have this mix of industry as well as academic representation in this webinar, both from NASA and Base Systems. So thank you for joining us. Yeah, and let's welcome Daniel.
Yeah, hi, thanks. I guess you gave the title. This was some work that I did with my co-author Lukman Arshad, and really kind of the motivation, is thinking about the safety of the airspace. So the first A in NASA is aeronautics, right? And so really what we were kind of trying to look for is establishing this aspect of safety of resilience, which is the ability of operators to dynamically prevent and mitigate hazards. Distributed situation awareness is, of course, a key aspect of this, because in the airspace, it is concretely what keeps pilots from flying into each other. So, this was our example in the paper. This was in IDETC a few years ago. We were thinking about this 2023 FedEx Southwest incident where the ATC clears a simultaneous landing and takeoff due to dense fog occluding the runway. But the FedEx pilot that was going to land saw the aircraft on the runway, so aborted the landing in time, notifying both the Southwest flight and air traffic control. So this was a near miss where a collision was avoided because of this distributed situation awareness property. So we had redundant pilot situation awareness filling in for the air traffic control situation awareness. Now, if you've been paying at all attention to the news lately, we've had more near misses than this. We've had actual crashes also in the airspace. So this is just an ongoing thing that I think is going to be important for us to understand and look at going forward. But it's also an important thing, there's an increasing push to try and automate parts of the airspace. And so we really need to understand these human resilience properties and distributed situation awareness properties in order to be able to replicate those things and hopefully improve them in our automated systems. So let's talk, this work it exists in a context. So of some existing efforts that we've been pushing forward in resilience. And so part of my team has been developing this simulation-based framework called FMD tools to evaluate a system's response to hazardous events, kind of in the framework on the left, where you can develop some scenarios, inject them into a system model, and then do kind of an aggregate assessment of the system's resilience to those scenarios. So yeah, this basically provides the constructs, and a big part of what we've been doing over the past 5 years has been providing these constructs to set up, run, and analyze what I like to think of as the game of hazard mitigation, with behaviors, which are like the rules of how the systems accomplish their goals, conditions, hazardous conditions that the system needs to mitigate, and then outcomes of how well the hazard was mitigated. FMD tools kind of operates on this principle of functional model propagation, where we've got basically a graph, except it's a bipartite graph that defines how the system is going to interact with other parts of the system behaviorally in a shared environment. And so I said it was a bipartite graph. Some of our nodes are functions. These are the behavioral elements of the system. And we have other nodes which are characterized as flows, which connect those functions. And so this is a aggregation relationship. Functions aggregate flows, meaning both functions have the same flow instance. And this was done initially to kind of represent tightly coupled physical interactions. We were thinking about fault modeling, which involves things like force balance, circuits, all of those things where you have a very tightly coupled behavior. If one thing changes in one function, it's going to be the exact change in the other function. And this kind of led us to a limitation, which is that what if the functions are people and the interaction is information? And this kind of tight coupling is maybe a bad fit to represent that, because your perception of information should not change the ground truth. And so we needed an idea of what a flow would look like to represent sort of a more loosely coupled relationship where we have kind of a separate reality and a separate ground truth. And so, yeah, kind of to figure out how to do this, we had to do some thinking about how to represent distributed situation awareness in the context of quantifying systems resilience. So if you recall, resilience is this ability of the system to mitigate hazards. We kind of came up with a generic model here of kind of what that task means in a distributed system, where we have some control that is being performed by various agents in the system that perceive stimuli, communicate via exchanges of information, and then take actions in a shared environment on controlled processes. So once we kind of figured out this picture, it then became a question, how do we represent these stimuli and exchanges? And it made us think about a little bit more, okay, we need to loosely couple our flows, and it had us create new classes of flows for that. So this was what we called a multi-flow class. And of course, that's the name of the class in the library, is multi-flow. And kind of the idea here is if you have multiple functions that are sort of representing those agents, each agent, it needs to get its own local state that is going to be its perception of the ground truth. And then we have a global one, which can be more the ground truth. And then this is set up as a network such that we can now see from the perspective of our global multi-flow object all of the different perceptions of that ground truth that exist across the engineered system. So that worked for perception, right? Because really all you need for that is separating ground truth from your perception of the ground truth. Communication's a little bit different. And the reason communication's a little bit different is because it's kind of like a network of information, and it flows through the system between different agents. And so we created this as an extension of the multi-flow class. So this is our comms flow class, and it basically added a couple things. One was this idea of inboxes and ports. So with inboxes, you can kind of have asynchronous one-to-many or many-to-one communications. That's sort of important if you're modeling air traffic control where everyone's just talking on a radio. And each of you are going to have different perceptions of that same channel that is being communicated one-to-many. And then we have ports to enable like dedicated information streams between agents. So, this is more like you have a chat window that is talking to a specific person that is only available to the both of you. It's not available to other agents. And so we kind of set up these theoretical constructs we can use, and then we wanted to demonstrate this in a relevant case study. And so for this, we developed a model of landing and takeoff at a taxiway. And so this is kind of a schematic representation of that. We've got a taxiway model that has aircraft, air traffic control, and then helicopters. And then those are connected via a requests comms flow. This is clearance, direction, and allocation of runways by the ATC. Then we have this location multi-flow, which is where the assets are and where they perceive the other assets to be. And then we have the environment multi-flow, which is just the airport and taxiway infrastructure managed by the ATC. And so here's a more fun looking little simulation on the right. And basically what we're modeling here is we've got aircraft in the air, we've got different places where they can land, we've got helipads for helicopters. They go and taxi to different gates they've been allocated. And then after some time, they go and take off into the air again. So it's a very kind of conceptual model of this, but it kind of gets the job done for the research question. And so now to model resilience in this model and show kind of how we can use these graphs to represent resilience, we looked at this aircraft clearance fault scenario. And so this scenario was the air traffic control gives duplicate landing commands to different assets who do not perceive each other in time. And so we can look at the effect of that on our flow classes. So this is our environment multi-flow class, and you can see in the ATC, they have overbooked this environment property. This leads to the ground truth also being overbooked a little bit later, which is how you see both of them, and degradations of how these are allocated and assigned. This then also propagates out through this requests comms flow. And so it's a little bit difficult to parse, but you can see these ones in the yellow have duplicate landing commands. And so we can see how that propagates out through this network to all of the different agents. And then we can see what the actual effect is in the result of a simulation. And in this case, we have a crash on the runway where one aircraft lands on top of the other because they were both cleared to land at the same time. So in addition to simulating the results of this distributed situational awareness loss, we were also able to quantify metrics such as number of degraded fields throughout various networks over the course of the scenario. Lots more details about that in the paper. We've got limited time, but I'll just take us to discussion and conclusion. Some of the takeaways here, we developed this capability to represent distributed situation awareness in dynamical system resilience models. This taxiway demo shows kind of the richness of this approach for modeling perception and communications errors. And our hope is this will let us better capture resilience in system of systems like the airspace. Some limitations, always some limitations. So the big one is that distributed understanding piece is real difficult to represent. So how do we represent thinking across a network of agents? It really just representing one person thinking is difficult. So what exactly is a good abstraction that we could use in a type of simulation like this, where it's kind of a high-level abstract thing, but we want to capture the appropriate level of richness? That's a real interesting question, and I'm not sure we're like totally have the right skills to do that. So if anyone has some ideas, please come and chat. And then another limitation is just the metrics used. Once you set these graphs up, you can quantify so many different metrics. And so I think a big question is, are there metrics that we can kind of track prior to the faults or prior to a hazardous outcome being realized that are sort of like precursors to that, that we could use for hazard mitigation? So thank you, everyone, for this work, and I will let the next person present now.
All right, great. All right, so let's move on to the final talk, which is by John Morris from University of Alabama, Huntsville. The paper is titled Unified System Modeling and Simulation via Constraint Hypergraphs. So let's welcome John.
Hi, thanks, Leah. So as Leah said, this paper is trying to pull together some resources for how to do unified system modeling and also simulation on there. We have a new framework that we're hoping can help bridge some of the problems that we see with distributed modeling, disparate simulation, and siloed information resources. I'm John. I'm an assistant professor coming into fall at the University of Alabama in Huntsville. See if I can get my slides working. Okay, so my problem statement here is that we have a lot of systems in this world that we need to understand as scientists, as engineers, as industry workers, but that we need to know how they're going to operate. It was Ross Ashby that said that a system is nothing more than a collection of variables, and these variables are all the things that we can know about a system. So if you look at this plane, there's all these different things that we want to know about it, domains that have information attached to them, that give us a bunch of different variables that we need to put values to if we want to know how that system is behaving or performing, or where that system is at some point in time. To get this information, we often provide a lot of different models, but because all these information is in different domains, our models can be really separated out and distributed. So we might have CAD models simulating the geometry, we might have electrical models doing the electrical systems, we might have systems models, flow diagrams, behavioral models, DES, Gantt charts, organization models, all these different domains that have their own modeling languages attached to them, and all these models are different views of the same system, but because they're in different softwares and languages and representation frameworks, they don't talk to each other. And as a result, the information that we want to have about this single system is often siloed and hard to access and understand. So what we're proposing in this paper is what's called a constraint hypergraph. This is a network that takes all these different models and deconstructs them into their primitive elements and allows us to bring them together and unify our system representations so we can see information across all the different domains and even simulate across those domains as well. So I'll quickly go through this and show some of the applications we get from this framework. So first off, really quickly to motivate how it works, systems are created by these variables. So here's our plane. We can have 4 different pieces of information maybe that we want to take from this. That's the economy, the fuel capacity, the color, and the name of it. Observations are things that I can observe using my own senses or maybe some sensors that I have on the field, but I can observe that this plane is gray, and that if I know my planes, that this is a Globemaster used by the US Air Force. That's something I can observe. Simulation, I'll give a very general definition for, is when we take things that we can observe and use them to set values for things that we are unable to observe. So from this picture, I cannot observe the economy or fuel capacity of this plane. But if I have maybe some database or some kind of model, I can use that model and pass it in my inputs of the name to predict the fuel economy or the fuel capacity. This is now a simulation. I didn't observe the fuel capacity, but I am predicting it via some kind of mapping from the name, my inputs, to the outputs of fuel capacity and economy. These mappings are algebraic functions, so not functions in the functional sense, like what are the functions of my system, but functions in the behavioral sense. So these are mappings from different sets as in algebra. Here we have a function that maps name to economy and name to the fuel capacity. I could have another function that might map the economy and flight capacity to flight range. This is some simple, actual algebra. I think we're doing division in this case. Here we see that this is a function with multiple inputs. So I have a product of this set and this set that come together, and I'm mapping every single combination of economy and fuel capacities to some kind of flight range over here. And that's, again, just simple division gives us this flight range. These functions are really the root of behavior. And it was Jan Willems that said that all functions let me go back. All behaviors in a system can be represented as functions mapping between the sets of information that comprise the systems that we want to represent. So if I'm looking at these systems, if I can break down my system into the set of states and the set of behavioral functions, I can get all representations of a system into those deconstructed primitive units. There's some nice things we can do with functions. Functions first off compose, because if we have a function with the same outputs as another function's inputs, those functions will always come together and give us a reasonable conclusion. So here, if I have the name of my plane, I can compose those functions in between, underneath, to get a mapping from every plane name over here to its flight range. And again, this is a simulation. If you tell me the name, I can give you the flight range based off the mathematics of the earlier functions. I can take these functions, and put them into a graph. And because functions can have multiple inputs or multiple arity, we can call this a hypergraph, where every single edge is a function. The multi-inputs to those functions come from different nodes, so all the nodes are states, and the functions map state to state. So every single function in here, or edge, tells me a model relationship that I can simulate in order to get some information. So if I know the load and speed, I can get out the fuel economy. And if you'll see from this that every single edge is a simulation, as well as every single path in the hypergraph becomes a simulation. So if I can put together a path, that tells me some combination of inputs and outputs that I can simulate and get information back out of my system without having to initially observe it. And so let me give you an example. Here's our map with all these different variables. There's, I think, 6 different paths in here that we can simulate. Each one of these has a different input. So the name, the load, the speed of the plane, each one gives a different set of outputs from composing different functions together. This is all the different functions that I can create on my hypergraph. By putting the functions into this kind of network framework, we get all of the different ways that we can simulate our system. This is all the information we can get out, all the different ways we can interrogate the system of interest that we're trying to represent. And so this is actually the notion of declarative simulation here. So in an imperative simulation framework, you put all your inputs at the top of your model and all your output at the bottom. Think of like writing a script in MATLAB. You put all your inputs at the top, and then you have a bunch of lines, and your script goes and converts your inputs to some output at the bottom. And that's great. That works really well for that one input to output mapping. But for declarative simulation, for something that we just want to be able to have the simulation returned for us, what we need is some mechanism that allows us to put in inputs and find a way to convert those inputs to some preferred output. And the hypergraph is what gives us this declarative mechanism. It allows us to arbitrarily rearrange functions and see all the different ways that we can put functions together in order to create simulations ad hoc. And this ability to create simulations is what makes this really powerful, rather than having to manually write, 6 different programs to simulate my plane model. Here with the hypergraph, I can just create the one constrained hypergraph with all my states and functions in it, and I automatically get out these 6 different simulations. We wrote a tool. I'm not trying to push a tool, but we did write a tool because we needed one to be able to search these hypergraphs. This is a constraint HG, and you can find it online. It's been published in the Journal of Open Source Software. But what it does is it does a breadth-first search on your constraint hypergraphs to allow you to do this declarative simulation. So the idea is that you take your models, you break them down into constraint hypergraphs. That's a functional-based model based off these sets. And when you have them all broken down together, then you can put them into constraint HG, represent them in using a Python script, and then you tell it the inputs that you know. So this is what I observe about my system. I know its size and how fast it's moving, and then you tell the program what you want to know, your output. I want to know where this plane is going to end up. I want to know how big it was at this point in time. I want to know who's flying at this moment. And then the software will search the graph to find the shortest length path from those inputs to outputs. And what you get out is this simulation that was automatically created for you, that does a simulation for you. And this has been really helpful for us. We've really enjoyed using this and put it to a variety of different systems. In the JCISE paper that this is based off of, we go through some of the structures of these hypergraphs. There are lots of unique details that have to be deconstructed, such as partiality. What happens if our sets don't always map over to our outputs? How do we handle that? Also, cycles are a big problem. Anyone working in networks knows that cycles are a huge problem. So how do we deal with cycles, and what does that mean? It turns out that cycles really imply that we have a dynamic system, something that the states are mutating or evolving over time. But we have to have ways of reconciling these cycles and unraveling them to do these simulations. And then also handling multi-edges. That's when we have multiple models that tell us how to solve for the same node. And these are competing models that we have to say whether or not I want to choose maybe a high fidelity or low fidelity model given some kind of preference structure. I go into more details about how these structures work in the paper, but I refer you to the paper in the interest of time to see more about how we deal with these different structures. Some of the applications that come from this are these CHGs provide great platforms for model-based engineering and also digital twins. These are ideas that we want to have these huge systems, whether it's a product or an organization or a research idea or in scientific natural system. And I want to be able to represent it and know information about it, but I need ways to bring all these different models together. In order to have that work, I need a way that can contain models that can work in different contexts. That means I can take a model and have it make sure it works if I plug it into context A, context B, environment C. I also need my models to be able to work with different models. If I have a model of a plane, and a model of a window, of an environment, maybe the weather, and a model of the runway, I need all those models to come together to create me a model of the greater system, the holistic system. And the hypergraphs give us a little bit of all of this. So first off, our nice cool thing about these hypergraphs is that they can cross between calculating software. A lot of the times the simulations that we want to run require really closed off proprietary software. But because we're going down to the functions, we can actually break these down into, break these calculating softwares down into the actual edges and make these functional graphs that allow us to do simulation that can cross between, in this case, we did a case study with ANSYS, MATLAB, and Onshape. And I'll show you an example of these graphs. Each color is a different software, but the software gives you a calculating function, basically, that you connect over the API. And then you connect that into the hypergraph via these nodes, and then you can query across these software. So if I have something in my geometry, maybe a moment of inertia or a center of mass that I need to calculate using CAD, 3D modeling. And then I have another thing that is kept in MATLAB because I want to do some complex optimization using their libraries. And I have another state, maybe my moment of deflection that's in my finite element tool. I can connect all those into the hypergraph, and then the paths that weave across these different softwares show me how to simulate all the different parameters, even across different software packages. And then here's my demonstration of this in an actual real form with a complex system. We worked with the Naval Postgraduate School to do a system model representation of their microgrid. They're building a digital twin out there. You can see the actual microgrid that they have set up. It's got different loads and solar panels, battery banks. They're trying to represent how resilient different naval bases can be to different disruptions. And so the Naval Postgraduate School has constructed this digital twin, or this real physical twin of a microgrid, and then they're trying to construct a digital twin of the other side to be able to do simulations on that physical microgrid. So what had been done at the Naval Postgraduate School already by several good researchers, a lot of master's students especially, were going through and making these large models. This is a complex system. There's lots of different things going on, interacting, lots of different states, and so there was lots of these models in MATLAB and Excel spreadsheets and scattered across different systems engineering frameworks, and they're all good models representing the system. All had really good mathematics going in there, robust models, but they were all siloed. And so what we did is we took them and we deconstructed them into this constraint hypergraph. That is finding the underlying algebraic functions, mapping between these sets that comprise the greater behavior of the system. And here's the hypergraph now. You can see it. It's very complex. There's actually only a subset of it. These aren't really meant for visual interpretation. So obviously we're not going to be communicating information about the microgrid just by showing a hypergraph to a human, but they are extremely computer readable, and that's where this gets really nice. So we can break down all these different types of modeling into this hypergraph. We have algebraic rules, we have dynamic stimulation here, database queries, file input output, stochastic models, that's probabilistic or even Bayesian models that you can put in here. Linear equation solvers, a whole variety of different things that kind of fall into this. We've also done examples with PID controllers, discrete event simulation. I showed you CAD and FEA, but all sorts of type of models. If it has a system and it's about behavior, it can be deconstructed into these constraint hypergraphs. And again, once it's in this state, what it provides you is this very declarative autonomous simulation. So now I can say, I want my microgrid to have this many solar cells and this kind of batteries. I want to know whether or not the weather being cloudy is going to impact my output, my power output on these loads. Am I able to meet the loads on my microgrid? And you just put in those inputs, specify the output, and then the path solver, that constraint HG software, is able to go through and construct the simulation out of it that gives you something like this, that tells you all the loads for a given condition. This is very autonomous. It's very nice. This was our big achievement, is that you don't have to write this simulation anymore. You just have to say, I've got my model, here's some inputs, here's output, and I get out this simulation. So in conclusion, these constraint hypergraphs give us a way to represent all systems, the states and the behaviors of them in a single framework that breaks down these silos, puts them all into a single language, and then once it's in that language, we get out the ability to do this autonomous declarative simulation. And if you'd like more information about constraint hypergraphs and how you can use them, as well as a link to the JCISE paper, we have some documentation and stuff at this link. I'll put the QR code up there. Thank you.
Thanks, John. All right. So in the interest of time, we'll quickly move on to the Q&A session. So this is a session where we get to ask questions. Hopefully, people have questions that you have saved up to ask for this time. But yeah, let me open this up to just free questions. If you have any questions, maybe raise your hand, please, and then I can unmute you or call you out. And feel free to chime in as well. That is fine as well. Okay, we have Samuel. All right, Samuel.
Yeah, thanks everyone for their presentations. I really enjoyed listening today. And I had a question about temporal network theory. So maybe, Giota, since you brought this up in your presentation, you could start. But if anyone has any insights here, I was curious, are temporal networks, are these kinds of problems always analyzed discretely? Like we have a series of static networks that we just solve in discrete time steps? Or do we ever solve them over continuous time analytically? I see some heat diffusion problems being solved with networks that are analytic in time. So I'm curious how we decide whether to analyze temporal networks discretely or analytically, if anyone has any thoughts.
I mean, Philip Knight, that is the mathematic lecturer from University of Strathclyde, is also in the call. In the method we have used them with time steps. We have time steps in the methodology, and obviously we had specific states that we were interested to analyze, and we use them with time steps. But yeah, I don't know if he has something more to add on that.
Yeah, thanks, Nyota. Can you hear me? Yep. So, yeah, I've had some experience working with temporal networks. Generally, it's discrete because we're working with data which comes from discrete samples. There are big issues in choosing an appropriate time step. Are you missing something by taking too big a time step, or getting spurious information by taking too small a one? But of course, you could also run a continuous model on a particular network. But yeah, my experience has been purely with temporal networks. You take them at discrete times, not necessarily evenly spaced. Of course, the number of nodes can change, which makes my approach, which involves matrix algebra, harder to do because you've got different sizes of matrices to combine. But yeah, that's I always see network theory as a way of escaping from calculus, and I'm happy to keep in the discrete field.
That's good. Thank you.
Yeah, I want to add a quick comment on top of the previous response. I had a very similar experience that it's indeed influenced by the data. For many of the temporal models, like the previous response mentioned, they require the network to be the same size to apply a temporal model instead of analyzing in discrete cross-section. You have different cross-section at different time step, right? So you can run the model multiple times on different cross-section. You can also draw insights out of it, or you can apply one temporal model on multiple networks in the sequential time sequence. But that sometimes being influenced by the requirement from the model, and you have to do a lot of assumptions. And probably, I remember one of the project we did is to really only analyze the overlapping nodes that always appear in multiple time steps, and assuming that the other nodes will not influence in the dynamics of the network, and in a way that we're able to apply a temporal model. I think that data perspective, I want to share my own experience that could be a decision factor that really influence how you choose the model in between.
So if I may chime in, just like say a few words about this and then go to my question. I think that's kind of like one easy trick that we can use when we have variable number of nodes, that we basically take the union of all the nodes in all the periods, and then some of them are going to be isolated nodes with no connection in some periods. So that way it's basically that solves that problem. So you can, but the tricky part is whether the dynamic is somehow endogenous. Basically, the nodes decide on the evolution of the system, or something that we just see from the data, like it's external. That's one of that actually creates, especially when there's an internal dynamic that determines the evolution of the network. That makes the dynamic network modeling challenging because there's like an internal causal force behind it. So I think that's a primary distinction: external forces versus internal dynamics. I also had a question from, I think, Daniel, about modeling of perception and the DSA in the DSA theory. So first, very interesting work. So my understanding is that currently you're basically drawing the perception of each agent independently from a common distribution, which is a great start. In many other work, I think, like we have a few projects in the lab where we're looking at perception as kind of like a network construct, meaning that the perception itself is under the influence of the perception of the neighboring nodes. in your work, do you think is that important? If so, do you have thoughts on how to implement the network diffusion of perception, not just the aggregation of the actions based on the perception?
I have to think a little bit about what you're trying to ask with that question. So when you say an adjacent node, or so what are you saying with that?
So if I interact with you, right?
Right.
My perception of an external reality or external, for example, risk that I see is
Mm,
influenced
mm,
by your perception. So
hmm.
over time, my perception also changes if we interact multiple times. So it's not just the action, but also the perception itself is driven by some kind of network diffusion dynamics. It's important in some scenarios. It's not important like it's right like the so just wanted to see whether do you have some uh, thoughts or some examples where that diffusion of perception is important in your context.
Yeah, so I think the big one would be, there's implicit and explicit like communications, right?
Mhm, mhm,
So, and this is, I think, part of the importance of that we kind of noticed in our model. We separate, okay, here's our explicit communications thing. They're all talking in a network.
mhm, mhm.
And then we have our perception, which is just like everyone seeing each other, right? And seeing how people are behaving. And so uh, I would say that, both of these things are important. Where I would kind of draw the boundaries, these are like how you write the behavior for each agent, right? The way we set up our network, it's like they each get this information, but then the behavior is then defining like, okay, how do you update your internal states based off of like how are you actually interacting with this network, right? And so those all just kind of become assumptions of the model, and it is a question, what's a good assumption versus a bad
Yes,
assumption,
yes,
right?
yes, absolutely. Yeah, yeah.
And I think it's real difficult once you're simulating people, right? what is the like correct abstraction there? And I think uh, so for this, when it, you know, some very very basic sorts of things, right? Is just like, well, okay, you are all connected in this network, but like there are constraints bounding what you're going to perceive in that network
Mm, mm,
that are not just like what we set up as connections. So, for example, we're looking at locations of everybody.
mhm.
I don't perceive locations of people far from me. We
Right.
may be in the same, we may all share this same location type of information that we all know, but we only really are keeping track of the people who are most close to us. And
Right.
so that was one thing where we had to just sort of in our behavior have a dedicated place, which is just like this is representing our perception of the closest person or closest other aircraft in the airspace.
Mm,
Whereas, and we'll update that based off of, just what's spatially close in the simulation.
mm.
Um,
Yeah, makes sense. Yeah. So, yeah. Thank you. That's so it's like as you said, it's like it all depends on what is a good assumption in this context. So the reason I'm asking this is we have an NSF funded project on creating a kind of like a theory of risk perception as a network construct. And then, for example, for the case of public health, so in some cases, based on data now, we see that up to 50% of agents' behavior can be explained through this network diffusion of perception of risk. So, which is like in that case, that's very important. In time, I think I was wondering. So we can continue that offline. So I would be
Yeah, absolutely.
Yeah, thank you.
Yes. So I want to be sensitive with the time. So we are 4 minutes over, but there is a question in the chat from John. So maybe we can make that the last question officially for the webinar. And then we do have an unofficial networking session for the next 15 minutes. So if you guys want to stay back and ask some more questions, I'm sure the speakers would be happy to if they are available to stay. So yes. John, do you want to go ahead and ask your question?
Yeah, thanks, Leah. It was somewhat related to what Babak asked Daniel already, but I was a little confused on how the flows slash multi-flows were set up, and especially how you were calculating them in the nice simulations that you were running. I was curious what manner you had found for connecting all these different functionalities together.
Yeah, so we've got our, it's very similar to your work actually. We've got our functions, which are not individual equations, they're technical functions, right? So they're just kind of bits of code that run certain behaviors. And then they aggregate these flows. And so the flows are a part of their definition. But then when we aggregate them as a whole, when we look at a whole simulation, we have a setup where you instantiate these flows, they get passed into these functions so that you have a shared aggregation. And then when we are doing multi-flows, we have this shared aggregation, but then each function creates its own local instance that is like both connected to, meaning a part of the definition of the overall flow, and a local copy. So there's all sorts of little software diagrams I can show you for this. It gets a little complicated, but the thing is, it's a really setting up a network within an object-oriented ontology where we can simulate these things kind of in isolation and then combine them in a graph and have variables that are in one function also appear in another function and propagate those variables between each other. And the flows are sets of those variables that have like a overall label. I'll just say overall label, right? It's like groups of things that all kind of would be used for communication of state, but that we can kind of look at a system level and give it meaning. So does that make sense?
Kind of. Are they bespoke between different functions? So if I wanted to integrate function A and function B, I'd have to create a specific flow class for that aggregation?
Yeah, so I would say if you have a function A and you have a function B and you have a function C, you can have the same flow connect those three functions, which is a little bit different. So a flow in our ontology is its own node. It's not a specific channel between two functions.
But it is a bipartite graph, right? Like you only have functions.
Yeah, that makes it a bipartite graph, yes.
Okay.
All right. Okay, so thank you everyone for your participation. Thank you to all the speakers. That was great. We really enjoyed listening to your presentations on this topic. We're so glad that JMD and JCISE could come together, and we hope that this conversation can keep on going. And hopefully this also gave you awareness that similar papers exist in both JMD and JCISE, and we can really merge the community together. So thank you everyone for your participation again. Again, we do have a networking session. It's optional, so if you'd like, you can stay behind. But yeah, that's the end of our webinar. Thank you for participating.
Thank
Thank
you.
you, everyone.
Thank you.
So, Leah, are we going to just stay here for the networking session, or?
Yeah,